everyone for coming. And yeah, it's I guess like when I was in my third year, I took a couple of classes from this department, but those were mostly online. So I've never visited this department. Is that okay? Okay. So today, what I'm planning to talk about is, as you see in the title, it's Gaussian certified unlearning and specific to high dimensions. Okay, so I guess every one of you have seen machine learning or have had a class in machine learning. Yes, no? Okay. So maybe we'll talk about machine unlearning and to be specific, this notion of Gaussian certifiability. Okay, so let's just begin. So these are the 5 things that I essentially want to convey. So at least I want to clarify what really I mean by machine unlearning. So that's the first thing. And there are essentially 2 things that we desire from a machine unlearning algorithm. One is what we'll call privacy or certifiability, and the other one is what we'll call accuracy or generalization capabilities. So these are the 2 things that we really want out of our unlearning algorithm. For example, similar to some kind of demands that you have for a learning algorithm. Okay, and then we'll describe like the very specific unlearning procedure that we have, and we will talk about some of the results. So that's essentially the thing. Now, maybe at the outset, what I am supposed to describe to you is what is machine unlearning. So, I mean, it's a very new field, and it's kind of developing very fast. So the definitions are kind of not really well settled yet. So maybe one of the interesting parts for me while developing this was really actually come up with, so to speak, the correct definition, and then the results, so to speak, followed. Okay. So let's start slowly with what is machine unlearning. And although you see 22 slides, I have essentially 14 slides. So hopefully I'll cover each in 4 minutes. So what is machine unlearning? So in broad terms, the idea is, let's say we all have, I guess, Instagram or Facebook account in some form, some online presence, and some companies collect our data. So that's the notation, let's say, we are going to follow, that companies follow, collect our data Z1 through Zn. I will be more specific in the next slide, but company have our data. And using that data, they have trained their machine learning model. Okay, so that means they have found out some beta hat. I will be clear more. And then what happens is, let's say I had a clash with my friend and I want to delete my Facebook account or something like that. So basically what happens after the data has been collected and the train model has been trained, then some users request their data to be deleted. And then what you are supposed to do is basically not just delete the data itself from the database as a company, but you are also supposed to tweak the model or change the model in such a way such that in fact the model parameters, the neural network weights, also forget the influence of those data points. So that's the idea. Okay, so that's roughly what we mean by machine learning. That means learning has already. Okay, the first thing to do is to remove the data from the database, and the next thing to do is like change the neural network model weights in such a way that in fact that new neural networks weights will also forget the presence of the removed data. Okay, so that's the idea. Now, okay, so one thing that we could try to do is, let's say maybe 1,000 of us requested remove our data to the company, some appropriate company. And then what the company did is basically retraining from scratch. So every time a couple of requests comes, maybe a single request or maybe a dozen of requests, then the company retrain the entire model. So it takes, it forgets the rest of the data, takes whatever data it has left, and it retains the entire model. Okay, so that's what we'll call, let's say, retraining. But as you can see, the current models are very large. So retraining is not really feasible. Okay, so retraining is not really feasible. So what should we really be doing? And that's essentially what is going to be called the field of machine unlearning, that do not do retraining, do something else, but still it should behave like a retrained model. So that's the idea. I guess the overall picture is clear. Okay. So in the clearest terms, I mean, I will be more precise with symbols later. So the idea is that we have to efficiently remove the influence of data points from a trained model. And there are two aspects that we need to be really careful, that we want to really keep the privacy of users, and that's there, so to speak, to keep them happy. And the other side is we also want the model to be really generalizable, or that means it should have the same generalization capabilities as it had earlier. Okay, so that's from the company's perspective. So we want to keep both of them happy. Okay, so that's the goal on a high level. Okay, so that's machine unlearning, but let's look at machine learning. So this is the setup. Okay, so machine learning, I mean, or statistics per se, let's say, for us will be this. So let's say the company receives a data set dn, which is some z1 through zn. So that is the data set that company has. And for this project or this slide, this entire slides, we will focus on the situation where we have the features are xi and yi's are the response. Okay, so that's a model that will focus on the kind of data set that we have in mind. Okay, so there's two things that we need to focus on the learning procedure. What are the two things? First, we will assume that the data generating process is IID and comes from something called a generalized linear model. So what does that mean? So that basically means that the response, the y's, depend on essentially x, but along some unknown direction of projection. So that's the idea. So y depends on x, the features, but it depends on some projection. So simple examples of generalized linear model includes linear regression and logistic regression and many other kind of so to speak models. Okay, so that's the statistical model that we'll focus on. But now the question arises that we are going to also impose, although this is somewhat from the theory perspective, is that we are also going to assume that this is how Google trained their data. Okay, so this is the framework that we'll follow. So the framework, I suppose maybe you're also familiar with. So this is usually called empirical risk minimization framework. So what happens there? So basically we have this data set Z1 through Zn, and we want to find an estimator. We do not know beta star, the true unknown, and we want to, so to speak, come up with an estimator beta hat. Now, the way to, so to speak, think about it, that how do I come up with an estimator of beta hat? So this is some sort of a belief that we should try to write down a loss function and minimize the loss function, and the minimizer is hopefully what is what we are going to call beta hat, and that is our representative solution for beta star. Okay, so that's the idea, but we should use the data because we have it. So that's kind of the loss plus a regularizer, as you can see. So this little l, which depends on the data, the ith data, and some sort of regularizer that we are also adding. Okay, so what do I really mean by L and R? So usually what happens, at least in the classical statistical setting, is this choice of L, the little l, will essentially be log of q or minus log of q up to a sign, because that's what we are going to call, let's say, negative log likelihood. And as you can see also in the title, that this is in high dimension. So it's somewhat known in some examples that just treating the log likelihood is not enough. It's sometimes I mean helpful if I have some prior information of where the true beta star might lie. We should also try to capture this using some loss, and that's the loss R regularizer. Okay, so that's so to speak the motivation. So at least the data generating process is clear, and which is generalized linear model and IID, and the learning procedure is clear. Okay, so this is the machine learning part of what I'm going to describe next. Okay, and comments are clear. Okay, so I guess this is clear. Maybe okay. Okay. So here we are slowly going into the framework of machine unlearning. So what is the ideal thing? So the ideal thing is some people requested that remove our data. Okay, we did remove them. So one way to do is basically output this beta hat slash m. Okay, so this is, so to speak, the ideal unlearning procedure, at least when we restrict ourselves to regularized empirical risk minimization framework. So this is what the company should ideally do. And in that case, it is, so to speak, clear that it does not really have any influence of the data points that were asked to be removed. Okay, so this is the ideal thing. But again, the problem is this is every time someone asks to remove my data, finding this optimization in really algorithmic sense is very difficult. So this is not really feasible. Okay, okay. So we need a way around, and that's where, so to speak, this thing called unlearning procedure appears. Okay, so I guess this is where I need to be a little more careful and describe it slowly. So okay, so here is, let's consider the company to be Google. So what happens is Google has trained its model on the data Z1 through Zn, and that's beta hat. So Google has received beta hat, or Google has beta hat, and Google gives me beta hat. Google also receives, after let's say some time, this data set dm. Those are the data points to be removed. So some individual have asked Google to remove our data, Facebook data, some data. Okay, so Google gives me these two things. That is, Google gives me beta hat. You take beta hat. You take, these are the individual's data points. You do whatever you would like to do, but give me an estimator beta tilde slash m. Okay, so that's what an unlearning procedure is supposed to capture, at least in our framework. Okay, so here you can see that you can play with this definition of whatever really you want. This a bar, which is supposedly what I'm calling as an unlearning procedure, to really have access to. So here I'm assuming that as an unlearning procedure, I have access to beta hat, which is the trained ML model, and the set of data points, or those individuals who have asked their data to be removed. You see two more notations. So one of them is so this is some auxiliary information, and it will be clear what the T of data points are. So that's one I'll explain. But for now, if you want to stick to it, just consider you have the trained ML model, the entire neural network's weights, and the data points of those individuals who have asked their data points to be removed. And that B that you see at the end for the unlearning procedure is basically some sort of noise injection. So that means we'll do some deterministic step like an algorithm, and then we'll add some noise. And that is supposedly the idea to have the notion of privacy. So in order to have privacy, one needs to add some version of a noise. Okay, so that's the reason we have the extra notion of a P. Just let me just go back a little bit. So here you see this beta hat is actually a deterministic procedure. Why? Because given the data set Z1 through Zn, actually beta hat is the deterministic function of Z1 through Zn. So that's what I mean by this is a deterministic algorithm. Okay. So throughout, I will assume the data set is like this. Generating process is generalized linear model, and the framework of learning is empirical risk minimization. Okay. So that's the learning framework. My task is, given these two things, to come up with an unlearning procedure, on which I will kind of impose some conditions. Okay. So far is clear. Okay. Okay. So these are the three things we demand. Okay. So in this set of slides, we won't really put too much emphasis on the efficiency part, although it can be said. We will focus on the other two things, and that's where interesting things actually happen, or at least our contributions are. So one thing that I want is to be able to capture privacy. Okay, so this is basically maybe is going to take maybe next 15 minutes, like in the next set of slides, to be able to explain in detail. But what do I really want? So you see there are two extreme things. What is that? So the ideal estimator is this beta hat slash m. So that's the ideal estimator, beta hat slash m, the thing this within relearn, the beta hat slash m. And on the other side, we have this unlearned thing. So this is what we are trying to construct. So we are trying to construct a bar. A bar is not yet present. It's just in abstract notation. We want to construct such an a bar. So what is one condition that I want? We want one condition that the distribution of a bar when acted on beta hat and dm, the removed data points, should be the same as when a bar is acting on the ideal unlearned estimator or ideal relearned estimator or retrained estimator. Okay. So here is where one thing should be clear. So here ideally this should without be the a bar, but because we have assumed that our learning algorithm is deterministic given the data. So if you do not take a bar, then this will actually be a deterministic point, and the question of indistinguishability of two distributions won't really make sense. I mean, it is indeed a Dirac delta, but for our purposes, it won't help. So that's the reasoning that we are going to compare these two things instead of the ideal retrained from scratch estimator, which is beta hat slash m. Okay. So maybe I'll wait for a minute because these are the two things that will appear every once in a while, or at least in the talk. Okay. No, so the algorithm is, I mean, once and for all fixed, let's say. And the data, like that, I have already assumed the algorithm is regularized empirical risk minimization for the Google doing its own training. And I have also assumed that the Google's data is coming from some generalized linear model. So those things I have already assumed. Now you can play with them as well. But for this part, let's say we are going to fix them. Now, once we have fixed them, I am saying we need to construct an unlearning algorithm, which is this a bar. I haven't shown you what really is this a bar, but I'm slowly trying to bid what do I really want out of it. Okay. So one thing is that Google gives me this beta hat, the trained model, and the list of data points to be removed. I would like to come up with some sort of beta tilde, which is this unlearned thing. That should be very close to the ideal retrained estimator or relearned estimator. But because our algorithm is deterministic, the original algorithm of Google, let's say, according to our assumptions, we have to do essentially, it's like a fair comparison is to compare with the outputs of a bar, okay, where you take the unlearned or retrained from scratch estimator, but there is no data removal request. So that's what I mean by this empty set phi. Okay, so there is no removal request that has appeared. It's just the ideal retrained estimator. So these are, to my understanding, two probability distributions, and I want to say somehow that I want these two to be indistinguishable. Okay, so these two are probability distributions. Okay, even condition on the data. Okay. Okay. Mm-hmm. Yeah, but that also will not allow, because in that case we will not be able to compare. So in earlier papers that has been considered, that compare unlearned with just beta hat slash m. But in this case we will have to we would have to compare these two things, because otherwise this won't be a distribution. What do I mean by that? Because when I say these two are distributions, what do I mean? Even you condition, then also I want these two to be probability measures or probability distributions. Okay? This one definitely is, even if you condition on the data, but if you remove this a bar, then this one won't be a probability distribution if you condition on the data. Uh-huh. Unlearning algorithm is randomized, but learning algorithm is deterministic. Uh-huh. Yes, yes. Yeah, it will add some noise. Yes, that's true. Yeah, that's true. Yeah, but the problem with even the original thing is it does not preserve privacy, right? The beta hat slash m is not really private per se. Like I'll explain slowly, but like because it like if some datas are like very large or something, beta hat will try to go along that direction. I mean, this is heuristic and vague, but I'm just saying. Okay, so at least this idea is hopefully clear. And okay, so that's one. And the other thing here on the second half, we will try to, so to speak, compare that the unlearned estimator, I want the generalization capability of that estimator, a bar dot beta hat dot dot dot, to be the same as, or same I mean, to be almost the same as the ideal retrained from scratch estimator. So here I'm not really applying a bar. So there are a lot of things you can play with, but this is what we fixed for this project. Okay. Okay, so this is on at least on a second high level I tried to explain, and then the math will appear after this. So there's two things we want to be as clear. From the people's perspective, I want indistinguishability, and from company's perspective, I want as accurate as possible. And our focus was on more sort of on the case where m is large, like this script m, the size of script m was large, not like 1 2, but rather growing with little n. So that was the thing that we are more sort of focused on. So at least these I guess requirements are hopefully clear. Okay, so so here so maybe how many of you have seen like ROC curves? Okay, so yeah, okay, so you guys are more familiar. Okay, good. Okay, so I'll try to explain. Maybe this is not the ROC curve that you've seen. I don't know, but okay, so let's see. So this is the step where we are going to formalize the privacy part. Okay. So let's build up slowly. So the next 3 slides would be like completely separated from machine unlearning and rather focused on a, I guess, classical topic in statistics, information theory, whatever you would like to call. So the idea is we have 2 probability distributions. Now the example that we have in mind is from the previous slide, this one. These 2 are the probability distributions, relearned and unlearned. But let's just abstractly write things down. Okay. So what is the idea? So the idea is we have 2 probability distributions, P and Q. Maybe before explaining, like how many of you have seen this trade-off function, or this is what I'm going to call as ROC curve. Okay, so maybe I'll explain. Okay. So the idea is the following, is that you have 2 probability distributions, let's say P and Q. Okay, you can call P0, P1, that's also okay. What you want to do is, you know, given 2 distributions P0 and P1 and a sample from either P or Q. You do not know which one it came from. So you have a sample, you do not know whether it is from P0 or from P1. And your task is to come up with a procedure to be able to say, okay, if the value takes in some subset of the space, I'm going to output 1. That means the thing came from P1 or Q. Or if it is the output is from some other subset of the space, then I'm going to output P or P0. So there's 2 kinds of errors that you can make in this procedure. What are the 2 kinds of errors? So the one kind of error is the reality is P0 or P, your output is 1. So this is precisely what do I mean by this. So the reality is P and my procedure is outputting 1. So you should think of as this phi or psi, whatever you would like to call, is let's say an indicator of a subset of the space omega or W. And so that's one kind of error. Reality is 0. My algorithm is outputting 1. The other kind of error is reality is 1. My algorithm is outputting 0. So that's the 2 kinds of error. 0, mine is 1. It is really 1, but mine is 0. My procedure is outputting 0. And 0, what do I mean by this? Precisely 1 minus this indicator. So that's what you think you should think of it as. But to be more formal, you have to allow phi to take any continuous values between 0 and 1, not just 0 or 1. Okay, so that's the idea. Now you have two kind of loss functions. You would like to minimize both of them. So there are multiple ways of minimizing. If you would like to minimize two, you can take a weighted combination, minimize. You can take the maxima, minimize. Here what I'm doing is I'm fixing one of the errors at level alpha and I'm minimizing the other one. So that's the idea. So here I'm fixing one of them, the next one, which is reality is P0 or P, and my algorithm is outputting 1, not algorithm, but procedure, let's say. And I'm fixing that to be some upper bound by alpha, and I'm minimizing the other error. So is this clear? Hopefully by now. Okay, so you have to, I guess, like work with it a little bit to be more comfortable. But basically, the right hand side, which is this alpha side, this is what is called type 1 error. And that's exactly the same as reality is 0, but my output is 1. And type 2 error is basically what I am infimizing, which is reality is 1 by my procedure is outputting 0. Okay, so that's the idea. So at least the definition is clear. Or no? Okay, so this is what I'm calling trade-off functions, or this is in some version, this is also the ROC curve. And the thing is, one thing maybe one would like to know. So this is an aside, which is okay. So this is an infimum over a class of functions. So is there an optimizing optimal phi that you can find? It turns out yes. In most of the cases, this will be given by the likelihood ratio. So this is basically given by some sort of threshold Z alpha, such that phi is going to be the indicator. Okay, but this is, as you can see, is a deterministic procedure. This only takes value 1 and 0, but in some cases you also have to take randomized procedures phi, which takes some values between 0 and 1 as well, like really in the open interval. But in general, I mean, most of the cases we'll deal with, but let's say if you assume both have continuous density and mutually absolutely continuous, it will turn out that this is good enough. Okay. So what have I said? I have said the following, that I have two probability distributions. I have defined a curve for you. Okay, so let me give you a picture. So usually these two curves. So let's say this is alpha. This is t of alpha for some choices of p and q. The curves that you'll see is this function from 0, 1 to 0, 1. This is how it will look, and this is multiple curves were drawn. Some are like this, and this is one blue is another example of a curve. Okay, so that's one. Now, how is privacy appearing here? Okay, so privacy appears here, or at least the notion of privacy appears in the following sense. But before going there, maybe let me ask, like, have people seen like epsilon, like pure epsilon differential privacy or epsilon delta differential privacy? Some version. Okay, do not worry. Okay, so okay, anyway, I'm not going to discuss that, but so okay, so I had two probability distributions P and Q, or P0, P1, and I described this curve. Okay, like fixing one error, minimize the other error. Okay. Now there's a small cute fact, which is this is not going to be relevant for us, but let me state it anyway. So this is definitely not our work, but this is has been proved in previous works. So the first is the following. So you ask, okay, we have these two probability measures P and Q. Let us vary them. So we take all possible Qs, all possible Ps, and we look at T of PQ. So this is some sort of like, I guess it's not so common maybe to look at, instead of one function, you look at a class of functions. So that's what we are trying to do. We are varying PQ, and in fact, the domain on which PQ lies. We are varying these three. We are getting a class of functions. Now we are asking what are all possible such class of functions. It turns out this is a very nice class, and this is what the statement is, that any function is actually a trade-off curve. That means there exists PQ such that f is TPQ. If and only if it is a convex, continuous, non-increasing, and it satisfies f of alpha less than equal to 1 minus alpha. So that means it lies below the diagram. So this is an interesting fact. but we'll not use it, but just so that we have at least one idea. Okay. Now comes this idea that, so we have a class of functions which are coming out of these pairs of probability measures. Okay. So we define this something called Blackwell ordering. What is it? So this is David Blackwell. What is it? So the idea is the following. So this is, we have two functions, let's say f and g. Both f and g are of this trade-off function kind, convex, continuous, dot, dot, dot. We say a function is greater than equal to the other if this happens. That means it is one of them is greater than equal to the other for all alpha. So it is definitely a partially ordered. Why? Because not two functions can be comparable. I suppose that is clear. So is this clear? Okay. So what does this say intuitively? Yeah, so this might be a leap of faith. Why? Because we are used to seeing comparing two probability measures, something like we are used to seeing maybe KL divergence. Okay, so there we compare two probability measures, something like a generic F divergence. There also we compare two probability measures. Here we have to do a little more extra step. What is it? We are comparing two things, but it's not one probability measure versus one probability measure. It's a pair of probability measures versus a pair of probability measures. Okay, and this pair of probability measures P0, Q0 has been combined into this curve. P1, Q1 has been combined into this curve, and we're comparing these two curves. Okay, what does this intuitively mean? So this intuitively mean the following. So the higher the curve is, the harder to distinguish it is. Okay, so the higher the curve is, the harder to distinguish it is. Is this clear? So that means if you have two probability measures P0, Q0 and TPQ0 is always higher than P1, Q1, that means P0, Q0 is harder to distinguish. Okay. So this is where you slowly see that we are trying to compare two probability measures with another two probability measures. And this is the ordering that we are going to see in our definition of machine unlearning, or at least the privacy aspect. And complete indistinguishability basically means the ideal thing, which is f of alpha equals 1 minus alpha, and that will be the case when P0 equals P1 or P equals Q. Okay. Yeah. So this is precisely the definition. Yeah. Yeah. So like that statement is the English statement, and the definition is precisely. Now you might want, why is it like, do I have another statement that is, so to speak, supporting it? So here is the statement, but this is obviously not us. So this is from David Blackwell. So this is the theorem. We'll explain it, but let's start with the theorem. So what does it say? So this is from 1950s, and it says the following. So Blackwell ordering is same as saying that the other two probability measures, the ones whose curves were higher, are actually Markov kernel, or Markov kernel applied to P1 and Q1. Okay. So these two conditions are actually equivalent. That I have four probability measures, one pair, one pair. I look at the curve. If this curve is higher than this curve, then this one, the one in the below, if you apply a Markov kernel, you will get the other one. Or there exists a Markov kernel. If you apply on the below, you will get the one above. Okay. So maybe one intuitive thing I should explain is an example. I don't have it here, but let me just state it. So think of it like this, that P1 and Q1, P1 is like delta 0, like the delta mass at 0, and Q1 is like delta mass as 1. Okay. So then they are easily distinguishable. Why? Because you see your output, if it is 0, it is 1, it came from P1. If it is 0, then it came from the appropriate thing. But now you apply a R, which is a Markov kernel. I assume everyone's like knows Markov kernel is same as randomized algorithm, if that makes sense. Okay, so that means it takes a probability measure, outputs another probability measure. So that's what it does in a linear way. Now R of delta 0, let's say it's uniform on 0, 1. R of delta 1, it's also uniform on 0, 1. That's the R I take. But then both are uniform. So P0, Q0 is uniform. Both are uniform, then they are not really distinguishable at all. So earlier we had a two completely distinguishable object, but after applying R, they become completely indistinguishable or very difficult to distinguish. So the intuition is if you apply R, it becomes harder to distinguish. And it turns out that that property is precisely captured by Blackwell order. So if Blackwell order is higher, then there is an R that is being applied. So it is some mixing that is happening, and mixing always creates confusion or increases confusion or indistinguishability. Okay, so yeah, it's a binary thing. So you like think about it for a minute. So okay, so yeah, that is true, but I mean in some sense. But so here is one fact. I don't know if I should write it on the board. So I don't have it here. So basically, can I write? I mean, the board if that's okay. Maybe the Zoom people will miss, but okay. So here is one fact. So this is one fact. So so any functional, it does not have to be Keil divergence. Like any functional of two probability measures, if it satisfies this, does anybody remember what is it called? Yeah, any functional that satisfies this is any functional that satisfies this for any P, any Q, any Markov kernel R is given by some functional of the trade-off function. So trade-off function is the key to almost anything that satisfies data processing inequality, or at least that contraction inequality. Okay, so that's really a powerful thing. Okay, but we are going a little bit aside, so let's just come back. So at least the intuition is clear that we have two probability measures, the unlearned, relearned. I guess that's written on that board, but it's not visible, no problem. So we have to compare with something. Okay, so that's like some sort of the base thing that we'll choose. So what is the base that we choose? So the base thing that we'll choose to compare our two unlearning procedures, the unlearned and the relearned, is to compare with the trade-off curves of a normal 0, 1 and a normal epsilon 1. So I want my procedures to be at least harder to distinguish than it is to distinguish between a normal 0, 1 and a normal epsilon 1. So that's the definition that is we are going to impose. Okay, but at least this hopefully is clear. At least the idea of trade-off function is clear. To pair, we can construct a function, and there is this idea that the higher we go, the harder it becomes to distinguish, and that is same as saying we apply a Markov kernel. Okay. So here is where actually the definition appears. Maybe it looks ugly, but let's just face it. So here is what we want. Okay. So recall we had two distributions. Okay, and when I say distributions, we always have condition on the data. Okay. Okay, so condition on the data, these two are distributions because we are adding some version of noise B, and we have these two distributions, and we would like to compare these two distributions with something. So the first definition of privacy, or what let's say we are calling certifiability, is basically the following: is that let's not worry about the inf for now. What we are saying is that the trade-off curve between these two distributions and the flipped version, because trade-off curves T of P0, P1 is not symmetric, it's not equal to T of P1, P0. So we have to take the minima, and that trade-off curve is actually higher than some other trade-off curve F. So this F we are going to take to be T of normal 0, 1 and normal epsilon 1. Okay, so we at least want our procedures to be better than distinguishing or harder to distinguish between a normal 0, 1 and a normal epsilon. So at least that is clear, hopefully. Okay. And then what do we want? We allow all possible removal requests of size little m. Okay. Now here you see this is one proposal of a definition. You can play with multiple proposals. You can put this out. You can change this f, because you know you are allowed to take any f as long as it is convex, continuous, ... two more. But basically this is what is the definition that we proposed. Okay. And before this definition of privacy, there were essentially two definitions of privacy or certifiability in the context of machine unlearning, but they were basically based on what is called epsilon differential privacy and epsilon delta differential privacy, and which also can be written in terms of this. But basically there the change is this function f won't really have a meaning. So it will look some ad hoc function. What do we mean by that? So epsilon privacy or epsilon delta privacy is same as being above some curve, but it's not going to be as smooth as this blue curve. It is going to be some you see this black curve, it's like some step function. So it's like some piecewise linear function will appear. Okay. And that is really not the thing one should be doing in high dimension. Okay. So that's formulation of privacy. So I think I took a lot of time, but let's, okay. Yeah. So basically, yeah, our definition captures all possible definitions of privacy. Here, f you choose to be f subscript some epsilon, and here you choose to be f subscript epsilon comma delta, where epsilon f epsilon has some function, f epsilon delta is some other function. But those functions, once you just look at it, you'd say this is probably not the thing we should consider. So this, I'm just like defining something more general, but basically you can restrict to any f. Soon I'll restrict to when f is Gaussian, like two pairs of Gaussian. Okay. Yes. Dm equals null. No, so okay, so no, so that actually that dm equal to null is probably not the thing. Here the thing is this will reduce to differential privacy or epsilon delta differential privacy with this choice of f. So basically this gives you, so in epsilon privacy or epsilon delta privacy, you have two parameters, epsilon and delta at max. Here you have a function. So you can vary a lot of things, and you can choose one specific function. I can write down, but maybe after the talk, f, which will depend on alpha, like as a function of alpha, and epsilon, and f epsilon subscript delta, f subscript epsilon comma delta, and that condition is same as saying that your unlearning and relearning satisfies epsilon delta privacy or epsilon privacy. Yeah, but the question is that f that you write down would be a linear, like stepwise function, and that does not really have a meaning in terms of, like, they are not really a trade-off curves between two nice distributions. Right? By two nice, I mean like two normal, two Poisson, those the ones that appear as limits of some sums of random variables. So that's what I mean. Okay. No, so that's part of modeling. So let's say, for example, if you're looking at like binomial random variables, but with p over n, then you would worry about like Poisson limits. But if you are, let's say, binomial random variables n, but binomial n comma p, but p is not 1 over n type, then the limiting object that you should be expecting is Gaussian. So similarly, in high dimension, the thing, okay, so this is revealing already, but in high dimension is, so here is where the idea is. So what is the procedure through which we are going to achieve privacy? So the procedure as of today, I mean, to my understanding, is we achieve privacy by adding noise. I mean, okay, there are more complicated things to be done, but in the world, let's say in the continuous world, in the RD world, not on discrete subsets, the way to do is to add just noise. So if you want to add noise, it will turn out, and this is not our work, this is shown in previous work, that if you add any noise in high dimension, what will happen is basically the trade-off curve will be comparable to a Gaussian trade-off curve. And this has been shown in the pure differential privacy literature. Like this is like unlearning literature. There is also this world of pure differential privacy literature. There, it has been shown that a large class of noise addition mechanisms actually are comparable to a Gaussian noise mechanism in high dimension as the dimension go large. So that's, so to speak, one justification that we should be using f equal to Gaussian when you're in the high dimension and in the continuous world. And what do we mean by large collection noise addition mechanism? It's mostly like log concave noise addition mechanisms. So that's, but f is part of modeling. You can choose whatever you want, and it should depend on like do some simulations, check what is appearing, and then based on that decide. I suppose that's maybe one way. Okay. And okay, so that's the definition. But definition, so formula, but you can see, you can play with other definitions and so on. This is what we proposed. Actually, at least capturing all possible generalizations of epsilon privacy, epsilon delta privacy, and there is also something called Renyi privacy and like F divergence privacy and many other things. All those are captured by actually this. What is T? Sorry, where is T? Sorry, I don't see a T. Oh, T is the trade-off function, right? No, so these two are distributions, right? So like I want, so I had two distributions, and this is what I demand. I've not yet told you what is this A bar that is going to satisfy all of this, but this is what I'm like imposing. This is what I want. Yeah. A bar is basically this P re is this, Pn is this. Yeah. So this is what I'm imposing. At least one condition. This is supposedly capturing user privacy. Okay, and this is again I'm emphasizing this is a much more generalization of epsilon delta privacy. Okay, or any such thing. And there the next definition. So this is generalization error divergence. So this is basically saying from the company's perspective. You don't have to worry about all of that. But basically, the real summary is the following. So this is not our proposal. This is the previous paper's proposal. So it says the following, that I really want that whatever my unlearning procedure is, that should have the same generalization error as that the ideally unlearned procedure. I mean, here also you can put A bar, beta hat slash M, comma B, phi, and so on. But let's say this is the definition that they proposed, and this is what we are going to also work with. Okay, so this is the definition, that on a new sample, and I'm going to take expectation with respect to the new sample. Okay, I'm conditioning on the data, and I'm going to average over the randomness of A bar and the new sample as well. Okay, and what am I doing? So this is beta hat slash M, this one, and this one is the unlearned thing. So I want this difference to be going to 0. So why? Because this is supposedly the ideal generalization error, and this is the generalization error that we are going to create. I want this difference to go to 0. So this is supposedly what, at least for our perspective, we are going to say that this is how we are going to preserve companies' generalization capabilities. Okay. So at least this definition is clear. So this is ideal. This is our thing. I want this to go to 0. But this is just the definition. We want this to go to 0. So these are the two things I demand on A bar. Okay. I want such an A bar that satisfies the thing, and the privacy thing, and also it satisfies this generalization error divergence goes to 0. So it's just a name. Do not worry about the name. But basically, this is what it is. Okay. So here is what the unlearning procedure is. It's not very different. I mean, very new or anything. But the interesting part, it is works, and I'll say why is it interesting in going forward. So okay. So what do I do? And maybe before describing the procedure, here's a disclaimer, because that's why we do not really worry too much about the accuracy, the efficiency aspect, because we are going to use a second order method. So we should be like lying low when talking about like real efficiency. So compared to first order methods, but anyway, it's better than the retraining. Okay. So Google has given me this beta hat, so I have access to beta hat. This is what I said by saying that I'll have some extra information. And what do I mean by an extra information? So this is, I should also be able to compute this quantity. So this is precisely what I mean by I should have some extra information. The T of dn you saw, I need that, and I also need the gradient at beta hat. So these are the things I need for me to for my algorithm to work, and that's why I demand that my A bar also should need to have some access to the real loss function Google used. Okay, so that's the idea. So this is the first step of the algorithm. I start at beta hat, and why am I doing this and not something else? I mean, okay, there are multiple other things, but why am I doing really this? Because this is some sort of one step going closer to the minimizer of L/M, and that is beta hat slash. So this is like a legit thing to do. Okay. Okay. So this is the first step, and this step, if we just stop there, it is good that we will really achieve generalization error goes to 0. But then we have to add noise, otherwise we won't really have privacy. Okay, so that's the deal. So we have to add noise, and this is the amount of noise we add, which is basically a Gaussian noise. But the question is, what is the sigma that we should be choosing so that we can have both sides? That means we are able to preserve epsilon privacy or epsilon Gaussian certifiability, and as well as the generalization error goes to 0. So that's the question. Okay. So I guess the unlearning procedure is clear. Now, okay, given the conditions that I want, you can come up with other unlearning procedures as well. For us, let's say we just did this, at least in this project. But you can see, you can play with the definition. Even you can play with the definition, the original definition of GLM. You can work with some other models. You can work with some other learning algorithms A. Given those two, we fixed, and then we decided on the definition of privacy. You can play with a little bit the definition of privacy, but I guess that is kind of well settled, I would say. I mean, at least it's but you can also play with the definition of generalization error. So these are the three things, a couple of things you can still play with. This is one example of an unlearning algorithm, and let's see whether that satisfies both of them. And obviously it should, otherwise okay. 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 Yeah. Yeah. Yeah, so this is where I will assume that I'm assuming that everything is happening in R to the P. Yeah. So this is in the continuous world. Yeah. So I'm not really worried about like discrete spaces. Yeah. That's true. Okay. So let's see. These are the two conditions I want. I just stated it. Basically, I want epsilon certifiability, epsilon Gaussian certifiability. With F, I replace it with G epsilon. And I already stated it. I have not put it in the slides, but basically a large collection of noise addition mechanisms will converge to some sort of comparable with some Gaussian privacy, okay, or Gaussian trade-off curves. And I want this generalization error to go to 0 as well. Okay, so here is the theorem. So it looks ugly, so let's not worry too much about it. But let me just state it. What I want to say is that there are some mild conditions that we need on our loss functions L and R. So usually these are separability conditions, some convexity conditions, smoothness conditions, and polynomial boundedness. These are the conditions I will require, let's say, for L and R. And I will assume that X is some normally distributed, normal 0 sigma or normal 0 identity, in fact, let's say. But these things can be like weakened, some of them. Okay. And then what happens is we look at this one step Newton estimator. So we take one step, we add a noise. Okay. And this is this careful choice of noise, because I want to choose epsilon to be given to us. So so this is 1 over epsilon, so that seems good. And we choose this sigma square to be r square over epsilon, where r is something that is actually diminishing. You do not have to worry about this, but basically it looks like some power of m divided by square root n. So what happens is the following, is that with high probability it actually satisfies epsilon Gaussian certifiability just after one step and addition of a Gaussian noise. Let me repeat. So it satisfies with high probability. What do we mean by high probability? So you recall we had a factor 1 minus phi. So this phi is 0. So we can find a choice of phi which goes to 0. There are several notations which looks complicated, but basically under some mild assumptions on the data and dot dot dot, which I can discuss offline, but basically this phi goes to 0. So with high probability, with a careful choice of this Gaussian noise B, I can actually achieve privacy. Okay, so the question is, does this help in the other world, which is to be able to achieve generalization error divergence going to 0? It turns out yes. Okay, so again with high probability, and this is the official, what do I mean by high probability, is that with high probability the generalization error divergence again looks like some power of n divided by square root n. Okay, so these are essentially the I would say the two things, but if you want to summarize, then the generalization error divergence of the true ideal estimator and the one step Newton plus a noise, that actually goes to 0 right after one step of Newton if the number of removal request is in fact polynomially growing with n, but up to some power. This is obviously suboptimal, but we do not, I guess we expect m to be square root n. That's the best we can do, but theoretically this is what we have. Okay. Why do you take one step and why not more? Yeah, that's a good question, because the more steps we take, the more computation power we need. So the question is, can I really just do with one step? So that's the question. Now here is where the interesting parts appear. So in a previous paper, it was claimed that under a different notion of certifiability, which is precisely under epsilon certifiability, 1 Newton step plus what they used is Laplace noise, because in order to achieve epsilon, pure epsilon certifiability, one has to add Laplace noise. So under addition of Laplace noise and epsilon certifiability, they actually showed that one step of Newton is not enough to guarantee this. And they said at least 2 Newton steps are required. But that was under a different notion of privacy. Here we switch the notion of privacy from pure epsilon to this epsilon Gaussian, and it turns out that under this notion actually 1 Newton step is enough, but here you just add Gaussian noise. Yeah, that's true. I mean, you have to do it twice. I mean, that's like, yeah, that's what I meant. Yeah, nothing beyond. Yeah, yeah. So that's yeah, that's what I meant. Yes. Yeah, L. Yeah. That's thing. Yeah. That's what I said. Like T of D, and I will assume. But basically, if you want to say overall message is the following, is that so okay. So here is the message. I skipped a little bit. So all our results are in actually high dimensional proportional asymptotics. So where I assume n and p are infinity and they are proportionally growing. That means the dimension of the unknown parameter beta star is proportionally growing with the number of samples. That's the setting we are working with. So all previous results except this one worked with p fixed and n going to infinity. And there the claim was under almost all possible notions of privacy, not all, but rather they focused on epsilon and epsilon delta. 1 Newton step is enough. That's what they showed in low dimension. And their proof failed when it was taken to be high dimension. So this paper showed all previous results fail in high dimension, and 2 Newton steps are required under epsilon privacy if I want to achieve generalization error to go to 0. So now we like reinstate the status back to where it was, but also in high dimension. But we change the definition of privacy, where I take a generic f, but for the specific theorem, we have f equal to Gaussian, like t of normal 0, 1 and normal epsilon. So that's about it. Yeah, that's all I had. The rest is this we just submitted to NeurIPS, so let's see what happens. Yeah, I guess the message is hopefully clear, except theorems do look ugly. I don't know how do I convey, but okay. Yeah, so that's yeah, but I guess yeah, I mean for me the interesting part was actually to be able to come up with this definition, because in unlearning everyone was following this epsilon and epsilon delta definition as like de facto, and but that's not really the case. So one has to choose this f accordingly to situations, because why am I saying this way? Because the only way we know how to achieve privacy is by noise addition, at least in the continuous world. So we need to choose the notion of privacy that really is optimally achieved by adding noise. And epsilon differential privacy, pure epsilon privacy, is not really optimally achieved by adding noise. So that's the problem. Yeah, that's true. Yeah. So yeah, so that was so the date was like 25th April, I would say. Like, so I was just reading this paper called Gaussian differential privacy. Uh, and so okay, so this paper, I guess I highly recommend this paper. So this paper is basically talks about, okay, so one result that really took my this is this result, that I guess everyone here probably loves like f divergence, scale divergence, and playing with them. So it turned out that like every such divergence can be written as a function of the trade-off curve. So that was one result hidden in the appendix of that paper, and so that was the starting point. Yeah. Yeah.